Also, in dealing with other transcendental functions, the incremental search method still keeps the same process. Check out how to approximate the root of an exponential function, here numerical solutions to C problems. Roots are x-intercepts, so they differ from solutions. From the name itself, one only needs to determine the approximate root by using intervals. These intervals are identified by purely guessing. The exponential function we will try to approximate is f of x squared times the Euler number e raised to x squared minus 4e raised to x plus 5. We're gonna look for a root nearest the origin at a negative site, and still we use 4 decimal accuracy and whole numbers for the initial values. Again, the first step is to search for the initial interval, where we are guided by having a root nearest 0 on the negative side. Start with x of 0, making 0 squared e raised to 0 squared minus 4e raised to 0 plus 5, which gives negative 9. Now let's try x of negative 1, which makes the function the square of negative 1 times e raised to negative 1 squared minus 4e raised to negative 1 plus 5, giving negative 3.753236. This is still a negative, so try another. Say we use negative 2. The function becomes negative 2 squared with e raised to negative 2 squared minus 4e raised to negative 2 plus 5, which results to 212.851259. This shows a sign jump, so we found the initial interval. From an illustration, we can check where the root is referred to. From the origin, move one x value back to negative 1 and have y of negative 3.753236. For x of negative 2, y is 212.851259. With whichever concavity we assume our curve this time, it will be no doubt that the root is so much nearer negative 1 than from negative 2. Since we already identified the interval between negative 2 to negative 1, we can assume a smaller increment of 0.1, and the reference limit is at x of negative 1. We use the upper limit, which means we subtract the increments. So the first iteration is negative 1.1, where the function then becomes the square of negative 1.1 with e raised to negative 1.1 squared minus 4e raised to negative 1.1 plus 5. This gives negative 2.273768. Take another increment with negative 1.2. The function then is negative 1.2 squared with e raised to negative 1.2 squared minus 4e raised to negative 1.2 plus 5, giving negative 0.126975. This is still a negative, so take another increment. By using negative 1.3, the function then is the square of negative 1.3 with e raised to negative 1.3 squared minus 4e raised to negative 1.3 plus 5, giving positive 3.068795. This is a positive, so the iteration is completed. And between the two of f of x's, we use negative 1.2 as reference for the next. With a smaller span of negative 1.3 to negative 1.2, we assume an interval of 0.01. From x of negative 1.2, we subtract another increment and have negative 1.21, making the function negative 1.21 squared times e raised to the square of negative 1.21 minus 4e raised to negative 1.21 plus 5. And this gives 0.137467. F of x is already positive, so we found the interval. And comparing the values, we use negative 1.2 again in the next iteration. With the current span between negative 1.21 to negative 1.2 and using negative 1.2 as reference, we use increments of 0.002. With negative 1.202, the function then is negative 1.202 squared times e raised to negative 1.202 squared minus 4e raised to negative 1.202 plus 5, resulting to negative 0.074956. When x is negative 1.204, the function becomes the square of negative 1.204 with e raised to the square of negative 1.204 minus 4e raised to negative 1.204 plus 5, giving negative 0.022461, still a negative. Try the next increment and plug in negative 1.206 into the function, which then results to positive 0.030424. The sign jump ends the iteration of this interval, and since we haven't earned that many zeros yet, we have the next set of iteration using x of negative 1.204. With an interval from negative 1.206 to negative 1.204, we then use increments of 0.0002 starting from the upper limit of x equal to negative 1.204. Subtract the increments and have the first iteration with x of negative 1.2042, where the function becomes the square of negative 1.2042 times e raised to the square of negative 1.2042 minus 4e raised to negative 1.2042 plus 5, giving negative 0.017191. The next increment makes negative 1.2044. Plug this into the function, and by computation, we end with negative 0.011918. This is still a negative. Next is negative 1.2046 into the function to make the square of negative 1.2046 with e raised to the square of negative 1.2046 minus 4e raised to negative 1.2046 plus 5, giving negative 0.006640. For x of negative 1.2048, work on the function to come up with negative 0.001358. This is still a negative, so we keep on subtracting in increments. Now we have negative 1.205, which makes the function negative 1.205 squared times e raised to negative 1.205 squared minus 4e raised to negative 1.205 plus 5, giving 0.003929. Finally, a positive, so we found our next interval, and we will be using x of negative 1.2048 as reference for the next. Now that we know the interval is from negative 1.205 to negative 1.2048, we use a smaller increment of 0.00002 into the reference limit with x of negative 1.2048. Subtract the increments, making the function into negative 1.20482 squared times e raised to negative 1.20482 squared minus 4e raised to negative 1.20482 plus 5. This yields negative 0.000829. Having the result as another negative, we should iterate again, this time using negative 1.20484, making the function negative 1.20484 squared times the Euler's number raised to negative 1.20484 squared minus 4e raised to negative 1.20484 plus 5, resulting to negative 0.000301. Work on another increment, making the function negative 1.20486 squared with e raised to the square of negative 1.20486 minus 4e raised to negative 1.20486 plus 5. This time the result is 0.000228. With the last turning out positive, we end the iteration and use the last increment as reference to the next. With the interval arising as negative 1.20486 to negative 1.20484, we also try the increment of 0.0000002. The first increment makes x of negative 1.204858, where the function becomes the square of negative 1.204858 times e raised to negative 1.204858 squared minus 4e raised to negative 1.204858 plus 5. This results to 0.000175. The next is with x of negative 1.204856, where if plugged into the function, yields f of x of 0.000122. At this point, it seems that we are near zero. Try another increment using negative 1.204854, where the function becomes the square of negative 1.204854 times e raised to the square of negative 1.204854 minus 4e raised to negative 1.204854 plus 5, yielding 0.000069. We already have 4 zeros, although when the fifth is rounded, it violates the requirement of 4 decimal zeros. So we work on more increments. Take negative 1.204852, whereby if substituted into the function, f of x becomes 0.000016. This is definitely lower than the required accuracy, but we also try another to make sure of the root. If we use x of negative 1.2485, the value for f of x turns out to be negative 0.000037. This definitely ends the iteration, but then the value is greater than the previous one. So we take the root as negative 1.204852.